So here, in order to find out the probability that, so we have 30 people, okay? And we have 166 possible dates for the birthday. And now, in order to find, we suppose that the birthday of these 30 people are all randomly distributed in these possible dates, okay? So now, in order to find the probability, to estimate the probability that two among them have the same birthday, we will have to count the number of cases in which at least two of them have the same birthday, and then we will divide that number by the total number of possible cases, okay? So for the total number of possibilities, it is easy to find according to the product rule, okay? So by the product rule, since each person among these people have 366 possibilities for a birthday, there will be a total of 366 to the power 30 possibility, okay? So do not attempt to calculate this number because it is an astronomical huge number, okay? So now we would like to calculate the number of possibilities in which at least two of them have the same birthday. And as you have seen in a previous example involving the subtraction rule, it may be more simple, maybe simpler to calculate the number of possibilities in which no two of them share the same birthday, and then we take the complementary of that. Okay, so you know that in order to create a set of birthdays in which no two birthdays are the same, we may consider a procedure. We first choose the birthday for the first person, and then we choose the birthday for the second person, which must be different than the first birthday. Okay, and then for the third person, we will choose another date which is different than the two previously chosen dates, and so on. So by the product rule, the number of possibilities for different birthday. Okay, so that different birthday. Okay, we will have the first one. We have full possibilities, and then the second one we have one fewer possibilities, and then and so on. Okay, and so the 30th person will have how many possibilities? Can you tell me? Maybe I should come to the cloud.
Recording in progress.
Okay. Chat. No, that was the. Yeah, that should be. So you can. type this. Okay, so the first one is this is the second one, so it should be 366 minus 30 and plus 1, so that makes 337. Okay, so now the probability that no two of them have the same birthday will be equal to this. Okay. And so this, you can write it as 1 times 1 minus 1 over 366, and so on. 1 minus 29 over 366. Okay, so this you can use your calculator or computer to, you can write a small script or a small program to calculate this. Okay, or you can even input it into Wolfram Alpha to get these results. Okay. So can someone quickly calculate this probability for me, please? Maybe you're better than me at using the calculators. Okay. Okay, so I saw that some of you asked why shouldn't it, why isn't it 365 plus 366? Because we also count the 29th of February. Okay, so let us trust your calculation that it is approximately 30%. So that means that the complementary probability will be about 70%, which is huge. Okay, so 70% is a rather large probability. So the probability that there exist at least two of them that share the same birthday will be around 1 minus this 0.3. Okay, so you can see that with those these four simple rules of counting, you are already able to solve the birthday paradox, which is not trivial, not intuitive question about probability. Okay, so these rules are simple, but they are powerful if you know how to use them. Okay, but of course, we will based on this rule, we will develop other tools to in order to solve counting problems or combinatoric problems in general. Okay, so thank you. So now we will move. Is there any question about this answer to the birthday paradox? Okay, so if there are no answer, then we'll move on to the next section, the pigeonhole principle. So the simple form of the pigeonhole principle says that if you have n plus 1 pigeons and only n pigeonholes, then there's at least one pigeonhole that is shared by at least two pigeons. Okay, so it is simple. So this is very simple for everyone to understand. So you in fact, you can say that mathematical knowledge is not required to understand this principle. Okay, if you have more pigeons than pigeonholes, then some pigeons must share a pigeonhole. Okay, so I guess that some of you may have heard of this principle in other names. You may have seen them as the Dirichlet principle or the drawer principle. You may have seen the variant in which instead of pigeons and pigeonholes, you have socks and drawers, or you have rabbits and cages and so on. Okay. So as the first example, so do you know what the function is? So a function is an application is a way to associate each element of the set on the left here to a value in the value set. Okay, so you may have seen some. You already know some functions, some more complicated functions, but here let's say that we have a discrete function. Okay, if we want to associate to each number in this set 1 2 etc. to n minus 1, sorry, n plus 1, to a value from 1 to n, then you can see that this is just another way to state the pigeonhole principle. Okay, so of course there are fewer values than the number of variables here, so necessarily there will be at least two variables for which have the same value of this function. Okay, injective here means do you know what injective is? Injective in Vietnamese is đơn ảnh. Okay, so injective means that if x is different from y, then necessarily f of x is different from f of y. Okay, so that means injective đơn ảnh. Okay. So of course you can see a trivial example that if you have more than 13 people in a group, then at least 2 of them should have the same month of birth. Okay, So this is a much more general example. So you cannot apply the pigeonhole principle to the birthday paradox. The difference is that for the birthday paradox, we were talking about the possibilities, okay? But for the pigeonhole principle, you are sure that, or in other words, you have a probability one, okay? So here, for pigeonhole principle, you are sure that something exists if we normally we use the pigeonhole principle is frequently used in problems to prove the existence of something. Okay, or maybe if you have a group of 27 people, then and you suppose that their names are all written in the English alphabet, then you can be sure that at least two of them uh, have the same starting letter in their name. But the difficulty when we try to apply the pigeonhole principle is that uh, in uh, in general we don't know in our problem what are the pigeons and what are the holes. Okay, so the most difficult thing is to detect is to is to see what are the pigeons and what are the holes. And once you already have the pigeons and the holes, then you can apply the principle. The principle is very simple, but the application is not trivial because it is hidden. Okay, so here is an example. Because in this example, it is not given explicitly to you what are the pigeons and what are the holes, and your task is to determine what are the pigeons and what are the holes in this in the problems. Okay. Now this example says that there exists a positive integer that is divisible by n. So here it says that for every positive integers, there is a multiple of n. A multiple of n is a number that is divisible by n. Okay, multiple in Vietnamese bội số. Okay, multiple. So for example, you can see that let's take if n is equal to 1, it is trivial. Okay, so let's see if n is equal to 1, we have 1 is a multiple of 1 itself. If n is equal to, so in this column we have n. If n is equal to 2, we can choose 10. 10 is divisible by 2. Okay, and 10 is written by only 1 and 2. With n, if n is 3, then you can see that 111 is a multiple of 3. It is equal to 3 times 37. Okay, so if n is equal to 4, can you tell me, can you find a multiple of 4 which is written with only zeros and ones? You see? So, for example, 100. Okay, and 1000 and so on. 5 also easy. So 6 is a little more difficult. Can you find a multiple of 6 which is written with only zeros and ones? Okay, so something being thank you. So okay, being okay. So you can see that you take the multiple of 3 here, you add a 0, and you have a multiple of 6. Okay, and for 7 it may be more complicated. But the thing here is we cannot verify that for every integer or every positive integer because there are infinitely many of them. Okay, but we can prove. So here, even if we verify this to up to for n up to 100, that doesn't qualify as a proof because in order to prove we have to use the logic and deduction. Okay, we cannot show that here are some examples in which it works so it was everything that doesn't it math doesn't work like that. Okay, so we have to use the knowledge that we already have in order to deduce the 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 conclusions that we want to prove. Okay, so here uh, you have the hint for you is to use the pigeonhole principle. But we don't know what are the pigeons and what are the holes because here the problem clearly it doesn't look like it doesn't look like the pigeonhole principle at all. So we need to create the pigeons and the holes ourselves. But normally when we work with problems about divisibility, it is frequent. It is we usually choose the holes as the modulo class, as the classes. How can you say you don't know that yet? So I will write it here so that we can. So here I will denote the holes by set. Okay, so we will divide every positive integers into sets, okay, into categories, or you can imagine that as a pigeonholes. Okay, so the first one will consist of the class S1 will be the set of integers which are integer m. Okay, so that m is divisible by n. Okay, or in other words, so this notation, do you know this notation? This notation reads text here. M is equal to 0 modulo n. Okay, so you read that notation like that. Okay. What does that mean? That means that the remainder of m divided by n is 0. Okay, so in Vietnamese, if we say that m is equal to 0 modulo n, that means that số dư thì lấy m chia cho n là bằng 0, đúng không? Okay. So in Vietnamese, right, so in Vietnamese, okay, so that is the definition. So the first pigeonhole will be denoted by 0, and so on. Or in general, you have S of I will be the set of integers m such that, so this vertical bar means such that, okay, such that m is equal to I modulo n. Okay, and since if we look at the divisions by n, then we will have the possible remainders will be the numbers from 0 to n minus 1. So in total, we will have, okay, so we will have n pigeonholes, and now we will need to find out we will have to create the pigeon. Okay. The pigeons, of course, will be the integers, but we will need to manipulate those integers so that so that to find something that is written with only zeros and ones. Okay, so according to basic arithmetic, you know that if two integers belong to the same class modulo n, okay, then their difference will be divisible by n. Do you agree with that? Okay. So in Vietnamese, okay, I will explain in Vietnamese. Tức là nếu hai số mà thuộc cùng vào một cái lớp đồng dư modulo n thì hiệu của chúng sẽ là một bội số của n. Okay. So now we look at the so now it becomes clearer and clearer that we are using the pigeonhole principle. Okay. So our pigeon, I will give you our pigeons will be these numbers. Will be the integers written with only the digit 1. Okay. So here what n plus 1 times okay, so we have n pigeons. We have n hosts. There are more pigeons than hosts. Then necessarily there will be at least 2 pigeons which belong to the same host. Okay. Maybe I will use text. Okay, so you have two pigeons, A k times and B, which is written with k. We have k, so we have L. No, maybe J times okay, which belong to the same host. That means that a minus b will be equal to 0 modulo n. Okay, so the fact that a and b are in the same class modulo n is equivalent to the fact that a minus b is divisible by n. Okay, and here you can assume that k is larger than j. So a minus b will be equal to so here how many we have k minus j 1 and we have j 0. Okay, so this number should be equal to 0 modulo n. That means that this number is a multiple of n written with only zeros and one. Okay, so here is the short version of the solution. Okay, so you consider n plus 1 numbers, and since you have only n possible remainders when divided by n, there will be two numbers in the same have the same remainder divided by n, and the difference of these two numbers is a multiple of n, which is written with only zeros and one. So you can try. You can try at home. You can try to use this method to find a number written with only zeros and ones, which is divisible by let's say 13 or 42 and so on. Okay, so do you understand this example? Do you understand this example? Okay, so if there are no questions, then we will move on. Okay, so you may see that we can generalize the pigeonhole principle to, in fact, to have more than two pigeons in the same hole. So if we consider a more general setting in which there are n pigeons, okay, there are n pigeons and k holes, then we divide n by k. We divide n by k, and we take the ceiling function. Do you know what the ceiling function is? So, for example, the ceiling of a real number is the integer closest to the smallest integer that is larger than or equal to this real number. For example, the ceiling of 0.1 is equal to 1. Okay, so if you draw the number line, so here are the integers, okay, and you have the number we have the number x here. Then the ceiling of x is the closest integer to the right of x. Okay, and similarly the floor of x will be the closest integer to the left of x. Okay. Okay, so here that it says that in a more general setup, if you have n pigeons and k holes, then there is at least one hole in which there are this amount of pigeon. Okay. So here is the definition. So here is a question. Suppose that you have a standard deck of playing cards, that is a deck of 52 cards, okay? And you want to take out a number of random cards so that among the chosen cards there are at least 3 cards of the same suit. So you know that you have 4 suits: the heart, the diamond, the what does it call, the leaf, okay, and the spades. Okay, so you have 4 suits, and you want to take out a random number, of cards randomly, but you want that there should be at least 3 cards of the same suit. And how many cards should you take in order to guarantee this condition? So basically, here is an application of the pigeonhole principle. But you can look at the pigeonhole principle in another way. Okay, so in order to guarantee that there are at least 3 cards of the same suit, you will try to you can try to find the worst case in which there are not 3 cards of the same suit. Do you understand? So, and then if you have the worst case in which there are no 3 cards of the same suit, and you add another card, then you are guaranteed to have at least 3 cards of the same suit. Okay, so that's the logic. Is it 27? Yeah, 9. Okay, 9. Okay, so some of you got the correct answer. So we look at the worst case. Okay, so in the worst case, there will be 2 cards of every suit. Okay, so the worst case, which does not satisfy this condition. In the worst case, you have 2 cards for each suit. First suit. So you have 8 cards. Okay. And then if you add another card, then of course you we then we will be sure that that we have some suite which has 3 cards. Okay. Okay. So you can look at the formula of the pigeonhole principle. Okay. You can look at n divided by k, and you replace k with 4 here. But I also encourage you to think about the approach in which you find the worst case and then you add 1. Okay. Now this one is a more complicated example in which you have to apply the pigeonhole principles 2 times in order to prove something. This is a famous problem. Okay, and if you go further in combinatorics, it will involve there is a branch of combinatorics which called the Ramsey theory, which deals with questions like this. So here you have a group of 6 people, and every 2 people are friends or enemies toward each other. Okay, and here you should note that the relation friends or enemy is mutual. Okay, so if 2 people are friends, then they are friends towards each other. So 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 each pair of people is either 2 friends or 2 enemies. Okay, so the question is that there's this example confirms that there is a group of 3 people who are either friends to each other or enemy to each other. Okay, do you understand the question? Okay, so maybe it is for this kind of problem, maybe it is easier to visualize the problem. So here we can use the graph representation of this problem. Okay, so let's say that we represent each person with a vertex of the graph, and each pair of people is connected by an edge, and we color the edge in red or blue according to the relationship between the corresponding vertices. Okay, so here, for example, this edge is red, meaning that the 2 people here and here are enemy towards each other, and this conversely, this is blue, meaning that this person and this person are friends with each other. Okay, so here let's fix this Mr. A. Okay, this person A here. So this person, we look at the relationship of this person with the 5 other people. Okay, we have 2 kinds of relationship, so necessarily there will be one type of relationship which has at least 3 edges. Okay, so here in this example, without loss of generality, we can assume that there are 3 three red edges. Okay, so here we have B, C, D. And now we have this situation where A is enemy to B, C, and D. So here there are two cases. So if among B, C, and D, we look at this triangle BCD here. If this triangle has a red edge, for example, if BC is red, then we have a red triangle in ABC. Here is a red triangle. That means that this is a group of three mutual enemies. Okay? But in the this is the case here. But if this triangle BCD doesn't have any red edge, then that means that it is a blue triangle. That means that here we have found a group of three mutual friends. Okay, so do you understand this example? This is a more advanced application of the pigeonhole principle. So you need to use the pigeonhole principle, and then you consider two cases in order to reach the conclusion. Okay? Um, to answer the question of Chu Baoming, the case of in the case of 26 cards with only two suits, you have 13 cards of the same suit. Okay, 13 is much larger than 3. We only look for 3 cards of the same suit, and now you have 13. Okay, but it is normal to ask a question like that, because if you when you start with the pigeonhole principle, it is not trivial to be able to distinguish between the holes. Okay, so here the more important thing is to see what are the holes. So here the holes are the suit. So we have 4 holes. Okay, so K is equal to 4. And we look for 3 cards of the same suit. So in your example, 26 cards in 2 suits, you already have 13 cards of the same suit. Any suit will do. Yeah. Okay. So so that was the last example of the previous lecture on basic principles of counting and the pigeonhole principle. Okay. So I propose we take a short 5-minute break, and after that we will proceed to the today's lecture on commutations and combinations. Okay, so let us pause.
Recording stopped.
Okay, I will resume the recording after the break. So 5 minutes. Let's
Recording in progress.
Okay, so let us resume the lecture. So now in this lecture, we will talk about permutations and combinations. So in Vietnamese, permutations mean the word hoán vị, okay, and combinations mean tổ hợp. Okay, we will see what are permutations and what are combinations. They're important objects in combinatorics. And then in the third part of the lecture, we will look at some nice identities involving permutations and combinations. Okay, so you can see that today's lecture consists of 3 parts. Okay, so let us start with an example. Who is talking? Okay. Okay, so suppose that we have a horse race in which there are 8 horses racing against each other. So if you want to make a bet on the outcome of the race, but you have no information regarding the previous performances of the horses, so that means that you can only bet in the dark. Then how many possibilities, how many ways are there for 3 medals to be awarded? That means that if the results are totally random, then how many possibilities are there to determine the first 3 horses in the race? And we suppose that there are no ties. Giờ chúng ta giả sử là không có kết quả hòa. Okay, can you see? In fact, you can use the simple product principle, product rule that we have seen last week to answer this question. Okay, since we suppose that the results are random, you can propose a procedure to determine the first 3 winning horses. Okay, so first there are 8 possibilities for the first place. Okay, so there are 8 possibilities for the first place. There are 7 possibilities for the first place, the second place, and the third place. So there are 8 possibilities for this place, and after you have removed 1 horse, there are 7 possibilities left for the second place, and then 6 possibilities left for the third place. So in total, by the product rule, you multiply these numbers with each other. and find the result. Okay. So a quick calculation will show that there are 336 ways for the first three places to be determined. Okay. And if you are interested in the total result of the race, then we can continue here. We stopped after the first three places, and if we continue into the last place, then we will have 8 times 7 times etc. times 2 times 1, which gives us more than 40,000 possibilities. Okay. So here, these numbers are, we are talking about the, you can look at this a different way. You can think that you have 8 horses and you try to arrange them in a linear order. Okay, so so you need not organize a race in order to determine here. You just take the 8 horses and you arrange them randomly. And so, in fact, we have counted the number of arrangement of the horses. Okay, so here in the second question, this number 40,320 is the total number of ways to arrange the 8 horses in a linear order. Okay? And this number 336 is the number of ways to choose an ordered set of 3 horses. And these types of ordered arrangement are called permutations. Okay, 1B. So here is the definition. So when we talk about a permutation, we always talk about permutation of a finite set. Okay, so this set here should be finite. You have it can be a set of integers. It can be a set of horses. Sorry, it can be a set of, I don't know, circles or squares or anything. Okay, so as long as it is a finite set. So a permutation is simply an arrangement of the elements, the arrangement of the entire set. Okay, so if you arrange the elements of this of that finite set, then you obtain a permutation of that set. And in this second case, we don't arrange all the elements of the set, but we choose R elements from that set and we arrange them. In that case, we have an R permutation of that set. Okay, so here are some. So in the previous examples of horse races, so here we have a set. So we have a set of 8 horses. Okay, so our set and the first question, in fact, count the number of free permutation. of that set. And the second question, count the total number of permutations of that set. And you can easily generalize this result to count the general number of permutations of a set, which is given here in this theorem. So you can apply the product rule to deduce that the number of permutations of a set of n elements is simply the product of the integers from n down to 1, or in short, we use this notation n followed by an exclamation mark is called n factorial. Okay, so which reads n factorial, or in Vietnamese n giai thừa factorial. Okay, and for the number of R permutations of a set of n elements, we use the in this course we use the notation P and R. So here, note that the total number, the larger number n is before, and the number, the size of the arrangement is after. Okay, so please bear in mind that this notation n factorial is global. That means that every document in the world use this notation, but the notation for R permutation may vary from book to book. But here we use the notation in the book of Rosen, which is this notation. Okay, so you can generalize the result of the previous example and find that the number of R permutations of a set of n elements is equal to the product of the numbers from the integers from n down to n minus r plus 1. So here, right, r times, okay, you start with n, and you descend r times, and then you get this product. Sorry, you descend r minus 1 times. Okay, and if we can write this product shortly using the factorial notation. So we got this. Okay, and of course there is a convention that 0 factorial is equal to 1. Okay, so this is the definition. It is convenient in calculation. Okay. And similarly, we adopt the convention that the empty permutation of a set of n elements is equal to 1. Okay, are there any questions? The permutation using the division rule. No, the formula for the number of R permutation. No, I don't think that it is division rule. No. In this case, no. Okay. So we have proved the formula for the R permutations using the product rule. But now, even though you see a division in this formula here, it is not because of the division rule. It is just a simplification of this expression. Okay. So the party of the proof is this part, this this equality. Okay, and this one is purely algebraic. Algebraic. Okay. Cái phần bên này chỉ là biến đổi đại số để thu gọn nó lại thôi. Cái phần thử chứng minh là cái công thức này sử dụng quy tắc nhân chứ không phải là quy tắc chia. Okay, so let's look at this example. So for those who do computer science, perhaps some of you have heard of the problem of traveling salesperson. So that is a classic example of an NP-complete problem, and which illustrates the what do you say, the what is called the combinatoric explosion of the state space in operation research. Okay, so suppose that there is a now, but now let's look at the number of possibilities of this problem. Okay, so I will talk about the problem of traveling person later. But now let's look at the smaller problem. So traveling salesperson. So historically, it was traveling salesman, but then because of gender equality, we starting from some moment we stopped using we stopped saying traveling salesman, but we say traveling salesperson, right, to be more neutral. And in this example, I even use saleswoman to emphasize on the issue of gender equality. Okay, so suppose that a salesperson has to visit 8 different cities. Okay, this person starts from her home city, and the cities are interconnected. That means that you have 8 cities, 4, 5. How many are there? 8. Okay. So this is the home city, and the cities are interconnected. That means that from an arbitrary city you can go to any other city. Okay. So you are free to choose your route, and the goal is to visit each city exactly once before going home. And in how many ways can this person make the tour? So you can see that you can. This is an option. You can go this way. Okay. Or you can also go this way in a more chaotic order. Or you can go in many other ways. And the question is, how many ways are there to make a tour like that? The only condition is that you visit each city exactly once. Okay, so you can see that if we list the cities in the order of visit, then you will have a permutation of the cities. Okay. Of course, the first city, the home city, is fixed, so we don't consider the home city. But if we, in fact, each way to make that tour can be identified with an arrangement of the 7 other cities. So in other words, each way to visit the cities, the number of ways to visit the city is equal to the number of permutations of the 7 other cities. So you can easily calculate the numerical result. 7 factorial is equal to 5040 ways, and you can try. You can so so no, there's not. Yeah. So you can see that it is a rather small number, but if you increase the number of cities slightly, then you can see that maybe double the number of city for 16. You can see that the number of possibility explodes. So the problem of traveling per person is an optimization problem. In fact, in the traveling per person problem, not every way to visit other cities are the same. That means that there are different costs of travel between the cities. So that problem aims to find the optimal way, the most the cheapest way to visit, to make a tour around all the cities. And since here you see that if you have if you have if you have n cities, then the number of possibility is n minus 1 factorial. It is a number which increase very fast with respect to n. It grows much faster than exponential. So, for example, if you have a problem of n cities, then of course it is not possible to compare all the possibilities in a naive way. So that's why this problem of traveling as a person is a difficult problem, because the cost of computation is very high. And here, in this example, you can see why this problem is a hard problem, because the the number of possibilities to consider is very large. You can take out your calculator and try to calculate 20 factorial, 30 factorial, and so on, to see what is the limit of your pocket calculator. And you can also see test the limit of the computer. You know that for those who are in ICT or who do computer science, you know that a personal computer like this has a processor of 64 bits. That means that it can store integer values up to 2 to the power 64, roughly. Okay, so you can use this information to see that if you calculate the value of factorials in a naive way, then what is the limit of your computer? It is not an exercise, but for those who are curious, you can try to see, and you will see that this function n factorial grow very fast. Okay. Let's see if there are questions. Okay, 7 factorial, very good, very good. Okay, here is another example. So we look at a string of 8 letters, and we shuffle the letters in this string. The question is that how many possibilities are there in which there is the substring ABC. Okay, so for those who will study cyber security, cryptography, you may encounter this kind of problems in the design of network, or in cipher schemes. In cryptography protocols, there are a lot of use of commutations. to generate random messages, random noise. So here is the question. You can try by hand. If you shuffle the letters of this string, then what is the, or in, you can rephrase this question that if you shuffle this string, then what is the probability to see this pattern ABC next to each other? Anyone has an idea? 5 factorial. Now, 5, so I see 5 factorial, 6 factorial. So maybe the result different, but I guess you all have the idea. Okay, so very well. So here the trick here is that you consider ABC to be one block. Okay. So if you want to A, B, and C to stay together, then we consider it a single block. And in fact, we have to count the number of permutations of these 5 elements. 5 blocks, A, B, C, single D, single E, single F, and single G. And of course, since there are 5 elements, there are 120 possibilities. So thank you. Yes, very good. Okay, so I see. Okay, so next to the combinations. Combinations is another type of another concept which is widely used in combinatorics, and you can see there is a similarity between combinations and permutations, but the difference is that in permutations we pay attention to the order of the elements. Meanwhile, in for combinations, we do not care about the order of the elements. In other words, if you want to talk in mathematical languages, in combinations, we only care about the subsets, okay? Because you know that in the set, the elements are not ordered. So here, as usual, we consider a finite set. Okay. So this set here, we always consider this finite. Okay. So if we have a finite set of n elements, and we will take out r elements from this set, then we obtain an r combination of this set. Okay, and we denote the number of r combinations of the set of elements by this notation. So C here, you can see the C here stands for combination, or a more globally accepted standard symbol is this notation, where you have n on top of r inside parentheses. Okay, so this notation is read as n choose r. Okay, n choose r means in Vietnamese, what it is in Vietnamese, you can say in Vietnamese you can say n chọn r, or tổ hợp chập r của n. Okay, so in Vietnamese you can also say n chọn r. Okay, n choose r. It's the same. And here you may have you may have been familiar with the formula for the number of R combinations of n elements. Okay, so it is given by this, but maybe it is instructive to remind you of the proof of this formula. So there are so here by convention you can adopt the convention that n choose R is equal to 0 if R is larger than n. Okay, so that is a widely used convention, and it will be given to you when necessary. Okay, but here for R comprised between 0 and n, we have this formula. Okay, and the proof so here is an indirect proof. We will use the will use the formula for the R permutation to prove this. Okay, so so it's written here, so I will give you here directly. Okay, so we will consider this procedure to create an R permutation of n elements. Okay, so in the proof of the formula for R permutations, we have selected the elements of the R permutations sequentially. Okay, so now we will do it in another way. We will choose a batch of R elements first, and then we will arrange them later. Okay, so we have two steps. So step one, we will pick out R elements without arranging them. Choose R elements. Okay, and then step two, arrange them. Okay, so here these two steps follow the step two follows step one, so we can use the product rule here. So the number of ways to do step one is, by definition, the number of R combinations of this set. Okay, so it is R n choose R. Okay, so for the first step, this is the number of ways. Okay, and for the second step, since we have already have R elements and we want to arrange them, there will be R factorial ways to arrange them. Okay, to put it together, we have the number of R permutations is equal to the number of, this is step one. Okay, this is step one. And this is the number of way to do step two. And then you use the formula for this, and then you put them together, and you get this formula for the number of R combinations of n objects or n elements. Is it clear? Yes, this one is the division rule. You can think of also think of it as the division rule, because each set of R element is used R factorial times when we create the R permutations. Okay, so very good remark, Kevin. Thank you. Okay, so here, this type of proof is called a combinatoric proof or a double counting argument. What does it call in Vietnamese? You can think roughly you count something in two ways. If you count something in two ways, and of course, whatever way you use to count, you should obtain the same result, right? So in order to prove an identity, you can count some objects in two ways. Each way will give you an expression, and the result should be the same. So you get an identity here. Tức là cái này gọi là kỹ thuật đếm hai lần. Các bạn sẽ đếm một số đối tượng nào đó theo hai cách. Thì kết quả thu được phải là như nhau, cho nên các bạn sẽ thu được hai cái mỗi cách cho các bạn một công thức. Thì hai công thức phải bằng nhau để chúng cho cùng một kết quả. Cái này là một cái kỹ thuật rất là phổ biến trong tổ hợp. Okay. That is called this is called a combinatoric proof, or more you can see double counting argument. There are many names for this type of technique. Okay, so here is an example. I guess you know about poker, okay? In poker, each player is dealt a hand of 5 cards. So suppose that you have a standard deck of 52 cards. Then how many different 5-card hands are there that can be dealt? In other words, if you take 5 random cards from a deck of 52 cards, then how many different hands can you have? So here, obviously, you don't care about the arrangement of the cards in a hand. Okay, so here we are looking at combinations instead of permutations, because here the order doesn't matter. Okay, so you can see that this is a trivial. So the answer is 52 choose 5 for the first question, and 52 choose 47 for the second question. But here's the thing. Choosing 5 cards from the standard deck is equivalent to choosing the 47 cards for the rest. Do you agree with me? So it's the same, right? So the number of ways to so the answer for the first question and the answer for the second question should be the same, right? So if you choose 5 cards to take out, or if you choose 47 cards to leave in the deck, then it's basically the same. The outcome is the same. So the number of ways to do either must be the same. And this is a general result. You have this. And basically, you can prove this identity by a combinatoric argument. So as I explained, you count the you have two procedures to choose 5 cards. Okay, so in the normal way, you choose 5 cards, or you can do it in the second way. You choose the card which are left. So since the number of ways must be the same, you have this identity. Or you can use the formula directly, because if you write this, then you have n factorial divided by r factorial n minus r factorial. Okay, and on the other hand, you have also n factorial divided by n minus r factorial r factorial. So they must be the same. But you can think of it as you can use the formula, or you can view it as two alternative ways to count the same thing. Okay. Okay, so that is proved by Jackson. Let me see if there are any message in chat. Yeah, they're the same. They're the same. That's the point of the slide. Okay. And now, this is a question I will. This is an easy question, but there's a lot of text, so I will let you read it in order to formalize what you have to calculate and which formula to use. Okay, so usually the exercises and questions that you will encounter in this section are simple, but sometimes the difficult thing is to understand the text form of the questions. The formulas may be simple, but it's the understanding of the question that is important. Okay, so anyone has an answer? So we have so here the question is to form a committee consisting of members from the math and the CS departments. So we want 3 teachers from the math department and 4 from the CS department. So in how many ways can we form such a committee? Okay, so thank you. So you choose independently 3 from the math department. So there are 9 choose 3 ways, and then you will choose 4 from the CS department. So there are 11 choose 4 ways, and then you by the product rule, you will multiply the 2 numbers together and get this huge number of possibilities. Okay, so even if you have quite not many members of the 2 different faculties, so 20 in total, but the number of possibilities is huge in comparison. Okay, so the formulas are simple, but we will see that there are many identities involving these formulas for combinations and permutations. Okay? So in this section 3, we will talk about the binomial theorem, which is a fundamental result in algebra, which is very useful when you develop polynomials and so on. So I suppose that you have seen this formula before in high school, right? So this is the formula for the development of what is called the Newton binomial. Okay, so you can see this theorem in various names: binomial theorem, or Newton's formula, or Newton's binomial theorem, and so on. Okay, but they all talk about the same thing. So here, it says that the expansion of the development of this expression x plus y to the n is given by this. So you can see that the coefficients of the in the development are related to the number of combination. Okay, so in fact you can prove this by induction by n on n, but here I present to you a way to anything in chat now. Yeah, okay. So here, one way to prove is to use induction on n. Okay. So I suppose that that's the way you prove this formula in high school. Okay. So induction prenup. Okay. Induction on n. Okay. But there is another way which is introduced here in order to prove this identity. Okay. So here, let's look at a term, a generic term of the right-hand side, which is n minus I x to the n minus I and y I. Okay. So you can see that in order to, in fact, when you develop this, you write the left-hand side as this product. Okay. And in fact, each term in the right hand side is formed by taking from each of these sum. You from each of these factor, you will choose either x or y. Okay. So here, for example, if you choose x in every factor here, then you will get x to the power n. Okay. So if you choose x from every factor except for the last one, then you will have x minus 1 n minus 1 y. Okay. But if you choose y from the first factor and you choose x from the others, then you also have this term. So that means that for a generic term, x to the power n minus y, y to the power I, there are many ways to choose, and each way to form such a term correspond to a way to choose n minus I times x from a factor. Okay, and y from the rest. So each term here corresponds to a way to choose let's say n minus I factors for from which we take x, and I are the factors for y. Okay, so do you understand? So in fact, each way here we give such a term, and the coefficient here correspond to the number of such terms, or in other words, the number of ways to choose n minus y factor x plus y here, from which we take x, and I from which we take I. And of course, that will lead you to the to the combination for formula here. So I will erase all this. So here it is stated here that the number of such terms is equal to the number of ways to choose n minus I x and I y from the sums here. Okay, so since the number of ways to choose is exactly n choose I, the coefficient of this which correspond to this term is equal to n choose I. Okay, so this is a combinatory proof of the binomial formula. And since these numbers appear in this formula, they are also called the binomial coefficient. Okay, so these are called the, in Vietnamese, hệ số nhị thức. Okay, binomial coefficients. Okay, so if you see binomial coefficients, you know that it is some n choose k. Okay. Now let us do some exercises. Quick questions. Now please give me the coefficient for x 6 y squared in the expansion of x plus y to the power 8. Okay, so let's go. Let's give me this number. Okay, so it should be 8 choose 2. And for those who are quick with calculation, it is 8 times 7 divided by 2, which is 28, as many of you have found. So very, very good, very well. Thank you. Yeah. So what about this one? So this one is more complicated because instead of x and y, you have some other coefficient involved. You have 2 and 3, and you even have minus. So let's see if you can get this one correctly. Okay, so here you can consider this as the 2x here play the role of x, so you can write it as 2x plus minus 3y. For those who are not familiar with this, you can write as this to the power 25. Okay, so I don't know the numerical value, so just write the formula. So for x 12 and y 13, you will have the coefficient will be 25, choose 12, but you have something in front of it. So you have 2 to the power 12 and 3 to the power 13, and minus in front of it because there is minus here, minus 3 to the power 13 is translated into this minus here. Okay, so very well. I see that is very easy for many of you. So good, so far so good. Okay, so this is the answer, and thumbs up. So we will continue this section next week. Okay. So I uploaded this the slide and the exercise list on Moodle. But for the exercise, you will have 1 week in delay. So this week and the next week, you will continue with the exercises on the basic rules and pigeonholes, and perhaps the first part of permutations. Okay, so are there any questions?
No question.
Okay, so goodbye,
Bye, teacher.
teacher.
Bye bye.
Okay.